Okay, so this is the beginning of chapter 2. We're just doing sections 2.1 to 2.3 today. And the first section here is on the atomic theory of matter. We're going to kind of go through some important principles and then how the model of the atom was discovered, essentially. So we have actually finally gotten to the level where we can see atoms. This is a very recent picture of iodine atoms on the surface of platinum metal. We got it using a technique called STM, or you might have heard of SEM, scanning electron microscope. This is scanning tunneling microscope. Okay, so this really is getting us to now be able to see on the atomic level, which is brand new, okay? So we can see images on the atomic level. Again, insane. So I have this little movie. Okay, hopefully you can hear this, but this is the world's smallest movie. You guys get the idea. So these are actually individual atoms, which is really interesting. And we can do something like that, like a stop motion animation with taking pictures of atoms. That's going to make astronomy relevant in the future, but anyway, moving on. So the modern atomic theory. So there's a lot that's brought us to the modern atomic theory, but there's a couple of laws that are extremely important. First being the law of conservation of mass. I know you all know the law of conservation of mass, which has to do with, there we go, matter cannot be created or destroyed, right? Matter cannot be created or destroyed. This actually governs almost everything we do in chemistry. Because matter can't be created or destroyed, we can actually calculate how much stuff we're supposed to make whenever we do a chemical reaction or things like that. So this is just an example here. When wood burns, right? Wood burns and it uses oxygen. And then we end up with ashes, carbon dioxide gas, and water vapor. Okay, and the mass of the oxygen used and the wood will equal the mass of the ashes, carbon dioxide, and water. Now, this is really hard to do because we would have to actually capture all of the gases being produced. We would have to know how much oxygen was used to burn, but these would be equal if we could capture everything. We could capture. Okay. So keep that in mind when we start doing math and stoichiometry. It's going to be important that the law of conservation of matter or mass comes into play. Okay, there's a couple other laws that govern exactly what we see in chemistry. The first being the law of definite proportions, which has to do with what it sounds like. The law of definite proportions has to do with proportions or ratios. And essentially it says that any given compound, so all samples of any given compound will have the same proportion or ratio, will have the same proportion of elements. Okay, so if you look at the picture example here, 1A with 8 B's makes 9 C's, law of conservation of mass. And then if I double it, then 2 A's would have to join with 16 B's in order to make 18 C's. Okay, so that's always going to be a ratio or a proportion. Real life application, if I'm talking about water anywhere in the world, if I have a pure water sample, it is always 88.8% of the mass is oxygen and the 11.2% is hydrogen, always. Okay, so if it's water, it's that same proportion. Okay, so the other law is the law of multiple proportions. And if you kind of think about what the name of the law means, this means that there can be different or multiple proportions. Okay, water is H2O, but you can have a different proportion of hydrogen to oxygen. You could do hydrogen peroxide, which is H2O2, which is a completely different formula, and it has different percentages, but it is still a combination of hydrogen and oxygen. So this is the law of multiple proportions. Essentially, nitrogen and oxygen can combine to make all of these different types of molecules, NO, NO2, N2O. So they can combine in different ratios. The law of multiple proportions says, however, that elements can combine in more than one way, like we just are looking at right now. So elements can combine in more than one way. Though they are always going to be related. Okay, so like nitrogen oxygen, NO is related to NO2 in some type of integer ratio. So elements can combine in more than one way. They will always be related through an integer ratio. And I'm going to do an example here in a moment. Okay. But if you do the mass ratios of them, you're always going to get a whole number ratio because nitrogen and oxygen is the same elements being used. All right. So here's an example. Okay. It says consider two separate compounds that are formed by only carbon and oxygen. Okay. So carbon and oxygen can make multiple compounds. We know we can have CO2. You can also have CO, carbon monoxide. It says the first compound has 42.9% carbon and 57.1% oxygen by mass, and the second has 27.3% carbon and 72.7% oxygen by mass. Okay, so different percentages, both carbon and oxygen. Is this consistent with the law of multiple proportions? So to test that, what we need to do is we need to find the ratio of carbon to oxygen or oxygen to carbon for each of the compounds. So I'm going to look at the first one. And it is 57.1% oxygen to 42.9% carbon. Okay, so if I actually divide those, I get that this is a 1.33 gram ratio. And then if I do the second one, 72.7% oxygen to 27.3% carbon, that is a 2.66 gram ratio. Now you might already be able to tell 2.66 and 1.33, those are going to be able to give us a whole number ratio, but to actually check, you compare the ratios, 1.33, and you get 2, which is a whole number. Okay, so any combination of carbon and oxygen should be able to give you a whole number ratio, and if not, then it doesn't follow the law of multiple proportions. So it will. Otherwise, you probably did the math wrong. So if it follows the law of multiple proportions, anytime you have different combinations of the same elements. Okay, now moving on to what the atom looks like. Okay, so Dalton is like the not the god. He is the like head of everything that came up with having to do with the atom. We use his research and his postulates or main themes for most of what we know about the atom, and then we kind of added on. Okay, so Dalton's laws, Dalton's theories are these 6 statements that each element is composed of tiny indestructible particles called atoms. All atoms of a given element are identical. The atoms of different elements are different and have different properties. Okay, so that makes sense. Most elements have different properties. Atoms cannot be created or destroyed. We already talked about that one. They can combine in simple whole number ratios to form compounds like H2O or H2O2. Atoms of the same elements may combine in more than one way to form different compounds, okay, again, like H2O and H2O2. And atoms are the smallest unit of matter that can take part in a chemical reaction. Now, as we've learned things, there's actually a couple of caveats to some of these postulates. Okay, Now, I will say these postulates had overwhelming evidence. Okay, so a theory, right? We call these Dalton theory. Isn't something that's just a theory in the sense that you think of it in regular conversation. So if you say, I have a theory, usually in regular conversation, that means, well, I think this might be the reason. A theory in science actually has a lot of evidence behind it. You can't call it a theory unless you have tested it in multiple different ways, multiple different times. Okay, so theories in science are actually have overwhelming amounts of evidence behind them, and we can believe or trust in them. Okay, a law, on the other hand, is something that just states what is true. So we just had the law of definite proportions, says this is always true. Okay, a theory explains why that might be based on evidence. Okay, so theories do have a lot of evidence backing them. Okay, so anyway, what we've learned since Dalton's day, our atoms are actually made up of smaller particles. So they're not the smallest particles, right? There's protons, neutrons, and electrons. Neutrons and electrons. And if we go even further, and this is not part of this course, these are all made up of quarks, which are even smaller, and we don't know as much about them. Okay. All atoms have the same elements are actually not identical because they can have different masses, right? You can have hydrogen 1 or hydrogen 2, deuterium or tritium, that's H2 and H3. They actually have different masses and they have completely different properties. So they're not identical. They can have different masses or properties. Usually, one isotope is going to be radioactive and the other ones are not. So they can be a little bit different. Atoms do not always combine in simple whole number ratios. As we start to get into organic chemistry using larger molecules, I would say a small whole number ratio, we're like 2s and 3s, maybe 4s. But you can have things like glucose, C6, H12O6, right? Those are big numbers. I would not call that a small whole number ratio. Yeah, you could reduce this, but that's not what the molecule looks like. This is actually what the glucose molecule looks like. So we're going to have a lot of organic molecules that have much higher ratios. Okay. And then finally, there are actually forms of elements that have different structures. So for example, carbon. If I have pure carbon, not all samples of pure carbon have the same properties or structures. Carbon can exist as graphite. It can exist as diamond. It can exist as charcoal. These all have different structures and they are called allotrope. So you might have heard that word before in science class. An allotrope is just something, same substance making it up, just has a different structure. Okay, on to 2.2. How did we get to our current model of the atom? We found out after Dalton, it's not just atoms. You can actually go smaller, protons, neutrons, electrons, all of that. Okay, so after Dalton came J.J. Thomson, and he did what's called the cathode ray tube or cathode ray experiment. Cathode ray tube, that's what this is a picture of. Okay, and his was actually pretty simple. Essentially, he shot a cathode ray, kind of like a ray of electrons, essentially, through this. Essentially, he shot a beam of what we now know are electrons through this tube. And notice he's got a negative plate here and a positive plate. And you notice that it always bent or attracted toward the positive plate. So that meant there had to have been something there that was negative. So essentially, he discovered the electron and the fact that it is negatively charged. Okay, so he's like, oh, there's a negatively charged particle within the atom. And so even if it was something going through, it was going to have a negative charge in there because it always attracted to the positive. Okay. At a similar time, Robert Millikan actually did the oil drop experiment, and he discovered the actual charge and the mass of an electron. This is kind of what that looks like. And I did link a video here. I'm not going to show it on here as though. Okay, so he found the charge and mass of the electron. Okay, so now we know the charge is negative. He actually found the value of the charge, like it's negative a certain number of coulombs, and that it has a very small mass. But he was able to do that with the oil droplet experiment. Okay, and then came along a lot of radioactive experiments, right? You've probably heard of Marie Curie and Pierre Curie. There are a few with Rutherford as well, but they found that there are radioactive atoms, right? We can get alpha, beta, gamma particles. They have different properties. They're all damaging in some way, shape, or form. We will do a whole unit on nuclear chemistry later, but essentially they discovered that there's alpha, beta, and gamma particles, besides just the atoms that we have been talking about. All right, and then Rutherford actually did quite a bit. You probably have heard his name before, especially if you've taken a chemistry class. He did the gold foil experiment. Gold foil experiment. And essentially what he did was he shot a stream of alpha particles, okay, we were just talking about alpha particles, at a thin sheet of gold foil. And if we had an atom that had a evenly distributed negative and positive charge, this is what we would have expected to see. However, that is not what we saw. We actually saw the alpha particles being deflected at different angles. And what that meant is that, well, since some went through and some were deflected, there must have been some dense center, the nucleus, that actually deflected those alpha particles, because alpha particles are pretty big, and some went through, meaning that there had to have been empty space in those atoms as well. So essentially what this showed is that there must be a dense region, that was repelling the alpha particles, okay? Meaning he discovered the nucleus, and also that there's vast regions of empty space. The atom is mostly empty space, no charged particles in there at all. So since that was the case, now this became our model of the atom, right? This is not a very good model because it doesn't show us relatively the size of the nucleus versus the electrons. But now we have this dense positive center and the electrons on the outside. The last piece of the puzzle really for this model was James Chadwick. He discovered neutrons, okay, which changed the mass. That's how we get different isotopes. And then we kind of ended up with this guy here. Now, remember that vast regions of empty space, so it actually looks a little bit different. This model is a little bit better, okay? Because this is so small, the nucleus is so small compared to how far the electrons can be, you wouldn't even be able to see it. It would be a pinpoint on this page if this was the size of the atom. So then if you blow it up, you can see the nucleus, which has some protons and some neutrons in it. The electrons are somewhere out here. They're actually not going in orbits or circles or ellipses or any of those things around the nucleus. They are somewhere in this general area. We'll talk more about that theory later as well. So the things you need to know, subatomic particles are, of course, the electron, the proton, and the neutron. And the things that we need to know about these electrons, protons, and neutrons are where they are, what their mass is, and what their charge is. So all of these particles are a little bit different. The electrons are, of course, on the outside. They're in what's called the electron cloud. And protons and neutrons are both in the nucleus. That's that dense positive center. Okay. Now, their masses, and usually we go on the terms of kilograms, right? That's our SI unit. So the masses are actually 9.11 times 10 to the negative 31st kilograms. Really small mass, right? This one is 1.67 times 10 to the negative 27th kilograms. and so is a neutron. These guys are very similar, a little bit different in mass, but not much. What I want you to look at is the big difference between the orders of magnitude of an electron and a proton and a neutron. So an electron is so much smaller, and protons and neutrons are about the same. So we kind of scale this actually to what we call the atomic mass unit. And so a neutron is about 1 AMU. A proton is about 1 AMU. And then the mass of an electron is so small that we call it 0 AMUs. Now, of course, it does have mass because all matter that takes up space has mass. It's just so small that we consider it 0. So when we're adding the mass of atoms together, it's really just the protons and the neutrons. Okay, last thing is the charge. Okay, we always think of an electron as having a charge of -1, proton having a charge of +1, and a neutron having no charge. Now, those are relative to each other, their charges. If you actually measure them in coulombs, our SI unit, you would get that the electron is -1.602 times 10 to the -19th coulombs. And a proton is exactly the same, but opposite. It's positive 1.602 times 10 to the -19th coulombs. Now, you don't have to have these numbers memorized. You should know that it's -1 + 1, 0, 1, and 1 for the atomic mass units, but you don't have to have the SI unit ones memorized, okay? All right, so moving on, the elements from the periodic table, you guys should be able to draw what's called a chemical symbol. Those are the letters, right? Okay, so a chemical symbol is 1 or 2 letters. All of the elements now have 1 or 2 letters. Usually, the first 2 letters in the name of the element, but that is not always the case. An important thing to note, though, is that the first letter is always capitalized, and the second is always lowercase. Okay, if you don't do this correctly, then you're going to get confused. For example, one that happens all the time is chlorine. So chlorine is capital C, lowercase l. But if you write C, capital L, that's going to be wrong. Or if you do capital C, capital I is carbon with iodine. So you have to be really careful. Okay, always do capital then lowercase. All right, now some of the ones that have weird symbols are actually from their old Latin names. So Na is actually sodium. These are a few that we use a lot, which came from the name natrium. That's how I'm going to say it. Iron is Fe. Its Latin name was ferrum. And lead, Pb, was called plumbum or plumbum. So that's where those came from, in case you are wondering, those old Latin names. All right, so we know the symbol. This is the atomic symbol. You write it large. And then we actually have some other pieces of the chemical symbol you need to be able to write. And those are the atomic number and the mass number. So when I say to write a chemical symbol, you need to have the letters. And then if you know the mass number, it should go in the top left. And if you know the atomic number, it should go in the bottom left. So the atomic number is the whole number from the periodic table. That's its number of protons. Okay, if you change the number of protons, you actually change the element. Okay, so it determines the element. Determines the element. So if you have a periodic table, like I'm going to provide you, then you can tell by how many protons what element it is, always. Okay, now the mass number, like it says up here, is the number of protons and neutrons. So you just add them together. So it's protons plus neutrons. That's going to be your mass number. Okay. Now this can be different for different elements, and those different ones are called isotopes, okay, which is our next word here. Okay, your mass number is always going to be a whole number because we say that a proton is 1 atomic mass unit and neutron is 1, so it's always going to be a whole number for you. And then we're bringing to isotopes, right? So isotopes are the same element, but they have different numbers of neutrons, so they have different masses. So same element, different number of neutrons. Okay, so I have some examples of isotopes right here. These are actually 3 isotopes of carbon. Remember, I said they can have different properties. So this was something that kind of went against what Dalton said. Carbon 12 versus carbon 13 versus carbon 14. Carbon, we use carbon dating a lot, and that's because the carbon-12 is not radioactive, whereas carbon-13, carbon-14 is radioactive. So we can actually determine how old something is based on how much radioactive material is there. So looking at these, the top left number, for example, in carbon-12, so this is one right here, is carbon-12. If I was to write it out, that's what I would write. The 12 is the mass number, so that means it has 12 protons plus neutrons. So if it has 6 protons, that means it must also have 6 neutrons. Okay, you change the number of neutrons, you change the mass number. Okay, so an element with 3 stable isotopes has 82 protons. Now, if you know how many protons it is, you can tell what the element it is. So go check out your periodic table, or you can also go to ptable.com. That's the one I use a lot of the time when I'm at home. And you would see that something that has 82 protons is lead, Pb. So it says to write the 3 stable isotopes that each contain 124, 125, or 126 neutrons. So if I was going to write these, they're all lead because they all have the same number of protons, okay, which is 82. So I can put my 82 down here. 82, 82. Now the thing that's going to change is the mass number. And remember, that's protons plus neutrons, so you need to add them together. So there's lead 206, there's lead 207, and there's lead 208. Okay, now again, you might see them written differently depending on how a question is asked. I can write lead 206 in a sentence. That would mean lead with a mass number of 206. All right, last thing I'm going to talk about is the atomic weight or the atomic mass. They mean the same thing. I know weight and mass aren't the same thing, but if I say atomic weight or atomic mass, I'm referring to the same thing. That is the number that has decimals on the periodic table. Okay, not the whole number. The whole number is the atomic number. The one with decimals is the atomic weight or the atomic mass. Now, if mass numbers are whole numbers, why would the atomic weight have decimals? Well, that's because it's actually an average of all of the isotopes for a specific element. Okay, so it's a weighted average of all isotopes, okay, for an element. All right, its unit is going to be AMUs, or atomic mass units, just like the mass number. And we can actually calculate this. So the atomic weights or the atomic mass is, calculation is the percent abundance, meaning how much there is for an isotope, times the mass of an isotope, plus, you just keep going for each isotope, the percent abundance of the next isotope, I'm going to abbreviate, times the mass of the next isotope, plus, and so on and so forth, all divided by 100. That will give you the atomic mass, the weighted atomic mass, okay? So essentially you do this for each isotope. Add them all together, you will get the number that's on the periodic table. Okay, you will get a weighted average. So essentially what this type of average is doing, it's taking into account how many are carbon-12s, how many are carbon-13s, how many are carbon-14s. Okay, so if we have like 90-some% carbon-12, which is true, then the mass is actually going to be more weighted toward 12. That's why on the periodic table it's 12.011, is because actually almost all of carbon is carbon-12. Carbon-13 and carbon-14 do exist, and they're taken into account, but most is carbon-12, so it's a weighted average. Okay, so you're gonna have to do some calculations like this on the homework. So I'm gonna do this example. So as example, chlorine has 2 isotopes. You can be chlorine-35 or chlorine-37, meaning their mass numbers are 35 or 37. Chlorine has a mass of 34, or sorry, chlorine-35 has this mass. Okay, so I have this mass and an abundance of 75.78%. And then 37 has this mass and an abundance of 24.22%. What is the atomic weight? Okay, so I'm going to use my equation. Essentially, it's the first percent, 75.78, times the first mass, 34.969, plus the second percentage, times the second mass. Okay, all divided by 100. Okay, now I want you to keep a couple things in mind here. First of all, your percentages should always add up to 100. If your percentages don't add up to 100, then you did something wrong when you were getting your data. Also, what was the other thing I wanted to say? You could change your percentages into decimals first instead of dividing by 100 at the end if you want to, it doesn't matter. But watch your order of operations. If you do your order of operations wrong, you're going to get an answer that doesn't make sense. So when you do this, and I recommend trying it right now in your calculator, you're going to get 35.46 atomic mass units. Okay, and that's actually correct for chlorine. It's really close to 35.46 on the periodic table. But this makes sense. So you should get an average somewhere in between 34.969 and 36.996. If you don't get a number between the actual atomic masses that I give you, then you did something wrong with your calculations. So usually when you do a math problem, at the end, I want you to pause and ask yourself, does this answer make sense? If, for example, I got 32 point something, that answer doesn't make sense. That must have meant that I did my algebra wrong. Okay, so always go back and make sure your answer makes sense. Mine does because it's in between my two numbers. So this must be the answer.